So far so good. It appears to be doing okay. It absolutely appears to be doing okay, but then there's a problem. And this is a new problem that I did not speak about previously. Now, let's get a little bit more practical. Of course, a formula that I should be giving you is that the velocity obstacle is nothing but a union of all O, velocity obstacle due to O. That's what we did previously. So velocity obstacle due to 1, velocity obstacle due to 2, velocity obstacle due to 3, velocity obstacle due to 4. We take a union of all the velocity obstacle, and thereafter I have a problem, and the problem is something like this. Imagine a practical scenario. It is the Prayagraj Mall, the only mall that we have. My robot, my agent is point, everything else is inflated, and after inflation, you've got this as a scenario. That's a mall, so there are a lot of people, and imagine their velocity vectors. Now the problem is you won't be able to find even a single free speed. Let's take random direction. Here I incur collision, here I incur collision, here I incur collision, here also 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 I incur collision. So there's absolutely no direction in which I can move such that I don't incur collision, and that's honestly bad. Wherever you move, you are colliding with some or the other obstacle, and therefore, what I do is I say something which is already said in a definition of reactive. So, how did I define my reactive way of working? I said I'll consider the nearest obstacles only. I'll consider the nearest 4-5 obstacles. I'll consider the nearest 4-5 people. I'll consider the nearest static obstacles near me. The term nearest was important. In potential field, if something was far off, the repulsion became zero. It vanished off. I'll have to do the same thing over here. So I say this is what is my decision making horizon. And I'll only consider things which are inside this horizon. Now, for starters, your decision making horizon is always based on distance, nearest 3 people, whose distance is closest to you as compared to any other. When you get more advanced, now you have velocity as well. And because you've got things like velocity as well, my decision making horizon will be defined in terms of time. So I say that incorporating this decision making horizon, I will only consider those agents or robots that are likely to collide within t time. And therefore, let's go to this figure again. This one is too far off, so time to collision will be very far off. It'll be extremely far off. And because it'll be absolutely extremely far off, I will not consider this thing up. So let's say suppose I aim to travel with velocity vector v. So the time to collision is equal to distance divided by speed, and this has to be less than t, which gives me that I can only select the magnitude of speeds. Now this is the first time I'm putting a constraint on the magnitude of speed velocity vector. Earlier it was always a direction of velocity. Now there's a constraint on the magnitude that I can consider. So put this here, and that's an added constraint. Where this is a constant which is given, it basically says how far do you plan, how far do you see, how far do you account for collisions. And now therefore my velocity vector becomes absolutely easy definition. So velocity obstacle for O is given by the set of all velocities v such that there exists a lambda such that q plus lambda times v intersection r, the spatial occupancy of O, this line and this vector collides, and I will incorporate for the speed, for the velocity by which the other agent is moving. So instead of taking v, I will take v plus vo. So that's what I said. It was minus vo and then I added plus vo. And along with that, I'll add this constraint that the magnitude of v has to be less than equal to dq comma q0 divided by t. And I'll of course give you another visual representation of this. So this is O, this is rho plus so this was my collision cone. This was my V. So the second thing that I did was this became my old velocity obstacle. So this was my collision cone of O. This was previously my collision velocity obstacle. Now what I'll do is, within this, I will eliminate speed such that the agent cannot collide. Now, extremely small speeds, if I take, the collision will not happen in t time. So extremely small speeds get vanished away. And this becomes my, the larger be the speed, the earlier will be the collision. So you see the lower magnitude of speeds have gone away, as well as what will happen if the obstacle was very far off, then virtually this entire region would have gone away, washed away. And this is my updated velocity obstacle for O. So collision doesn't happen within a t amount of time. That is my velocity obstacle O, the updated definition. Remember that the more far I place this, the more region from here will get clear. If this is infinitely far off, virtually this entire region is clear and only extremely high speeds will be there. And if you have multiple obstacles, so let me have a few obstacles. So that again becomes a collision cone. The velocity vector is VO2. So this will be the collision cone. And similarly, if I have a O3, this will be the collision cone. And say it's traveling at VO over here, so this becomes the collision cone. So anything in red is danger. Do not select your velocity vector like that. Anything in red is an absolute danger. Now, for the first time, let me talk about reachable velocities. And let me tell you why. Because it may appear that let's select this velocity, but the only problem is the magnitude of this is 1,000 meters per second. You cannot travel by that speed, by the way. It's not possible. So when I cannot travel by that speed, how come? Now it may appear 0 is the best speed. I can reach that. Everybody can travel by 0, but the only problem is that I'm currently traveling at 25 meters per second. From 25 meters per second, you cannot go to 0 meter per second in an instant. It's not possible. You'll have to apply an acceleration that is like really, really hard. So that's what I say, that I have got constraints. So my first constraint is that my magnitude of speed is limited. I cannot travel more than 100 kilometers per hour. My other constraint is that my acceleration is also limited. And because my acceleration is limited, I say my acceleration is between minus a min, or let's say between a min, which will definitely be negative, to a max. If I'm traveling with a speed of Vt, that means, and this program is operating in a frequency such that my time period between every 2 consecutive cycles is delta t. So I know my speed can be, between Vt minus a min to Vt plus a max. Similarly, my angular speed has constraints. So my angular speed can be between omega min, which will be negative, to omega max. Let me not consider angular acceleration to make it simple. So that means if I'm currently at theta t, this has to be Vt plus 1. Okay, if I use time at one place, what am I doing? T plus delta t. Okay, my bad. A min delta t, a max delta t, my bad. Okay, so my angular speed is also limited to the same region, and so that's another constraint that I have. And because of that, if my current orientation is theta t, so my orientation has to be limited to theta t plus omega min delta t and theta t plus omega max delta t. Now, let's plot this thing kind of graphically. It's becoming weird that I've got speed constraints on my speed because I cannot travel more than a certain speed. I've got constraints on speed because of my acceleration limits. I've got constraints because of my speed, which does give me constraints on how much of maximum can I turn. So suppose again this was r at a position q, x, y. And alongside it, let us consider that this is my current speed v, and this is my current orientation. Now this says that the velocity vector that I finally select will have to follow the angular constraint, so it cannot be outside this region. And similarly, my magnitude of speed is limited. So my magnitude of speed is limited to this region. So this is kind of Vmax. And this is my, so this is Vmin and this is Vmax. That's possible because of these constraints. So I cannot go outside this because of my speed constraints outside this triangle. And I also cannot this thing over here because I've got angular constraints. So anything which is inside this region, let me put this region a bit more clearly. So this region is the only one that I can attain. So anything in blue is okay. Those are the only reachable speeds. So I call them as the reachable speed, the reachable velocities. If you have a bit of kinematics, you can actually plot this thing up. So now what I do is I just show you the reachable speeds, let's say as a cartoon. So these are my reachable speeds. So it cannot be inside this red and it has to be inside this blue. So blue is the reachable speeds, blue is the reachable velocities. So it cannot be inside red and it has to be strictly inside this blue. That means my speed selection is limited to this. And that's what I say, the reachable avoidance velocities, reachable avoiding that is equal to the reachable speeds this is this blue diagram minus the velocity obstacles. So this one is shown in blue and this one is shown as red, of course. So I have to select a velocity such that it is in this region. Those are my constraints.